story of my interest in space has been very closely tied to the fate of a pair of twins named Opportunity and Spirit. Back in 2003, I was finishing up an undergrad internship at MBA, and Opportunity and Spirit launched and started their journey to Mars. A journey that took them about a year and a half to get there, going through all sorts of fascinating stages along the way, from the rocket launch itself to the spacecraft maneuvers in orbit and insertion orbits, and then the entry into the Martian atmosphere, and finally down onto the Martian surface. And it's those operations on the Martian surface that I've been following closely and that I'd like to talk to you about today. So here we see them coming up on the red planet, entering in through the atmosphere. So you may, I'm sure a lot of you know a lot of this story already. You might be more familiar with the more recent landing of the Mars Science Laboratory, Curiosity. They had this crazy landing scenario with a sky crane that lowered the rover down. I'd argue that our Opportunity and Spirit's landing was no less crazy, where they instead had these airbags that would inflate, and the rovers would just drop down and tumbled across the surface before they started their driving. So these rovers have been a great success for anyone who has any interest in space exploration and specifically Mars exploration. They've given us access to great areas of that planet, and it's been an amazing technological achievement, specifically for NASA JPL, but all sorts of other work that has gone into the space industry and research leading up to these types of achievements that we can make. So here we see the clamshell opening up. Rover opens up. And finally, we're going to see in a moment the moment of truth for me, where a wheel touches dirt. And this has been the aspect of space exploration that has been my focus since about that time. So, see the solar panels opening up. We'll see the mass deploy. Wheels will antenna. See the wheels open up. So here we see opportunity for Spirit taking their first look out onto the Martian surface. Crash. But you get the idea. So a long, torturous road to get there, but eventually they get there. And here we see the driving that Opportunity has managed to do. So since landing, at this point, over 12 years ago, I believe, Opportunity is still operating. Just a couple years ago, it completed a marathon's worth of roving with its record time of 11 and a half years. I'm not sure qualifies it for the Boston Marathon, but still, it's the first time, it's the longest roving that humanity has achieved to date, and has explored all sorts of areas of Mars, from small to large craters, and done tons of groundbreaking science for us. And its twin, Spirit, also had a very productive and interesting mission, and traveled and traversed great parts of Mars as well. But Spirit, that mission has already concluded. And we'll see in a moment why. You may already know. But to give you an idea, a sense of reference, the next photo is going to have the front wheels of the rover from the vantage point of the cameras on the rover. And this arm at the front of the rover, we'll see a shadow of that arm as well. So this is what happened to Spirit in 2009. We see one of the front wheels here, sort of regular on the surface, and another one buried deep into soil here. And this ended up being the one event that proved, to be a mission-critical failure in the end for Spirit. It had already achieved some incredible, success in its mission, but if it hadn't stuck in this soil here, there's a possibility it would still be roving, just like Opportunity, and continuing to produce planetary science for us. So this has been the motivating problem for me. So this happened, I mentioned that the Spirit launched right around when I was doing an internship in the space industry. So this happened just as I was starting my PhD. And I was looking for something to be interested in, something to focus my career on going forward. And this has been the driving problem for me in terms of how rovers deal with dirt. And dirt is something that in the space industry and in space research is the one thing no one wants to touch. We have clean rooms. I build dirty rooms because some spacecraft need to interact with dirt. And the effect of space and planetary environments on that dirt is an interesting question for me. So one of the things we do is we have the privilege of visiting the Canadian Space Agency's Mars yard, and we run rovers equipped with sensors where we try to detect the different types of terrains that we're encountering and try to predict which of those soils might pose a hazard for the rover. So we deal with this in two ways. We try to predict hazardous situations, or we try to come up with ways to deal with hazardous situations that we encounter. So this is Scarab, one of the robots I worked on during my PhD. And this is driving in a material, it's called phyllite. It's actually an industrial material that it's a remnant of coal power plants. As these little balls of ash that create spheres that are hollow spheres. So you end up with something that looks like soil, but actually has much lower density. So we were trying to mimic Martian effects by having this low density soil. And we would have this robot drive in it, and you could see it sinking down into the soil. And then we had these new types of motion mechanisms that would inchworm our way out of that predicament. So we would start by driving down into these situations where we're stuck, like Spirit, and use these novel mechanisms to get ourselves out of those situations. So just a plug for an idea of something I'd like to build here in Montreal at some point in the future. Sort of a Scarab 2.0, a more elaborate vehicle that can do the same sort of motion as we saw in the video before, but also much more complex motions, including turning with the same sort of inchworming type approach where you plant some wheels and drive the others. And actually with the mechanism to enable that, we could then do all sorts of trajectories, designing wheel-by-wheel trajectories for a rover, so that you can plant certain wheels and drive other parts of your robot independently. So these are some of the things that I like to think about and like to work on when looking at this problem, the Spirit entrapment problem. Now, at the time when Spirit got stuck, NASA JPL was not ready to throw in the towel, and they put together a large campaign called the Free Spirit campaign, where they were trying to free Spirit. And one of the things they did was they built a mock-up with a sandbox of the type of soil that they thought that Spirit was stuck in. They put it on the same sort of slope and angles that they were getting from the instruments that the Spirit was in. And they were trying different maneuvers to see if the rover might be able to drive its way out of this, if they try all sorts of things. And they would do this with what's called the SSTV Lite, which is a model of the rover, but with the equivalent, with a reduced mass to mimic the equivalently reduced weight in Martian gravity. So essentially, this test was done with a rover that was 3/8 or about a third of the mass of the Mars exploration rovers themselves. And this is, of course, something that anyone would try to do in this sort of situation. But looking at this campaign and following it closely, it really raised a question to me whether this test is valid. So we're mimicking the reduced weight of the rover on Mars, but is there anything else that we're missing? So there's atmospheric density. Anything else? Curious? Anyone? So the weight of the sand. The effect of gravity doesn't only change the weight of the rover, but also the sand. In that earlier video with Scarab, I talked briefly about how we tried to mimic these reduced densities of the soil or we tried to use a reduced density soil to mimic this reduced weight of the soil. This is a problem that is really hard to do without being right there on Mars. It's a really hard problem to tackle. So forgive the sort of entry-level physics, but not a lot of, like I mentioned, not a lot of people in the space, area spend much time thinking about dirt. So I'd like to show that thinking about dirt is not much different than all the other physics that we do for all the other, all the other aspects of space design. So everyone's seen this problem, the canonical block on a slope. So just using regular Newton's laws, we can of course find the equation F equals ma. And if we want this block to stay stationary, we set that equals 0. But the interesting thing is that if we combine these two equations in a particular way, then what we find is that the coefficient of friction is equal to the tangent of, in this case, the maximum slope that we could set this angle at. Now, this is a standard result, but it's something that is actually directly applicable when we work with soils. This angle and its relation to friction. When we pile soil, there's a maximum slope to which we can pile it. That's called the slope's angle of repose. In a more general sense, if it's buried under other soil, we can also refer to the friction angle of a soil. And essentially, we have this exact analogy where if we put a If we put another grain of sand on this slope, if this slope were to be hypothetically higher than this angle of friction for the soil, then it would tumble down, and what we would be left with is a pile at that particular angle. Now, the question that comes into the soil is that soils have these frictional properties, and friction is what really drives a lot of these interactions with soil. But the tricky part about friction and its application to soil mechanics is that friction depends on gravity. The normal force that is assumed in any sort of frictional contact is, of course, mass times the gravitational acceleration, if we're thinking about vertical normal forces. And this friction is related to this friction angle, but the friction is also related to the normal forces and thus gravity. So the question that's taken for granted in soil mechanics is that this friction angle is something that's just constant. It's a constant for a particular type of soil. But there's a question that comes up, which is, because of this relationship to gravity, is it possible that these friction angles are different on Mars than they are here on Earth? Even if we took the same soil to a different gravitational environment, does it behave the same way? So, I'm not going to spend too much time on this slide, but this is a standard soil mechanics problem, where we apply a load to an area of on top of the soil. Typically, for soil mechanics, they deal with things like foundations. So they'd be building a foundation, say, on this soil that has some properties. But we could think of this also as the wheel of a rover pushing down on soil. And the thing is that the bearing strength, or the ability of the soil to resist this object pressing down into the soil, is of course very closely related to the amount of normal force that we apply. The less force we apply, the less likely we are to sink down. But it's also very tightly related to this concept of the friction angle. And it's not also just the friction angle or the friction of the soil particles directly below the object that's being placed on the soil, but it actually propagates out to regions of the soil that aren't under our direct influence, not sort of vertically below our object. So you have these areas going out to the sides. And if our gravity is different, will this sort of failure plane be the same in these areas as it is here on Earth? So is this as best as we can do in terms of a test, or are we missing something when we do this kind of experiment? So when we look at the two options that we have, or what we're trying to compare to one another, in one case, what we're doing is we're staying in a constant gravity environment, and we're just reducing the weight of the rover itself. So the normal load that's applied through the wheel. So in this case, if we have Earth gravity but we reduce weight, then what happens is that we reduce this normal force, and since our traction is based on friction that we can generate with the soil and within the soil, our traction goes down. So that's one of the bad things of trying to drive in extraterrestrial environments, is our traction is going to be lower because our weight has gone down. But in the situation where we're mimicking it on Earth, what also happens is that if we reduce the weight, then our sinkage into the soil also goes down. If you press less, then you'll sink down less. And the resistance that's applied to a wheel is very much related to how much that wheel is sunk into the soil. The more sunk down you are into the soil, the more resistance you are going to have to your forward driving. So in this case, if we're doing this test on Earth, in Earth gravity, with a reduced weight rover, then what we're doing is we're reducing our ability to gain traction, but we're also reducing the resistance that's being encountered through the wheel. So we kind of have some effects both helping and hindering us relative to just a wheel driving, like a full weight rover driving on Earth. Now, in the actual situation where we're going to Mars and we're reducing the weight of the rover, but we're reducing the weight of the soil as well, because we're reducing that weight by reducing the gravity as opposed to by reducing the mass in the weight equals mass times gravity equation. In this situation, of course, weight is reduced, so we get the same reduction in traction, where we have, because it again relies on friction. But now the question is, what happens to our sinkage? Does our sinkage also reduce in this Martian environment? We're applying less weight, so maybe our sinkage reduces, right? But the strength of the soil itself, because there's less gravity, also goes down. So that's an important question. What happens to sinkage when we're in this reduced G environment? So before I answer that question, I'm going to take yet another quick diversion here. And again, this is probably well known to most people in the room, but being a public conference, I just want to give a little bit of background. So here's a famous Canadian, and he's in 0G, right? Well, I find that there's a misconception sometimes with this concept of 0G, because being in low Earth orbit on the International Space Station, the actual amount of gravity acting on the space station relative to us here standing in this room, it's only reduced by about 10%. In terms of the distance from Earth reduces that gravity just to about 90%. The reason that they're weightless is not because it's 0G, it's because they're in free fall. It's like, falling on an amusement park ride. Except that they're falling so far that they're constantly falling. They're falling so far because they have such high horizontal velocity that the curvature of the Earth keeps falling away from them. So they keep falling, but the ground that they're falling towards also keeps moving away. So that's essentially what being in orbit means, right? So that's all. That review in orbital mechanics is all just to say that we don't need to mimic different gravity levels. We don't actually have to be in different gravity levels. We can achieve that through trajectories. And when we're in orbit, we can mimic weightlessness, which is like being in 0G, even though we're not in 0G. And we've already heard a lot today from Dr. Wickremshing and from Steve about parabolic flights, and that's another way that we can mimic reduced gravity. So by flying these trajectories, if we want to do micro-G or weightlessness in these aircraft, essentially fly these parabolic trajectories where you spend a certain amount of time essentially in free fall in the airplane and you feel weightless. Or if you just modify that trajectory, not make it quite as steep, you can set a particular equivalent gravity level or equivalent weight in that aircraft. And so there was some work done by a group in Japan where they did this, where I got this figure from, and I'll show you some of their results in a moment, because they did something similar where they took a wheel, put it in soil, and put it inside one of these aircraft. So, as a quick diversion, I know you showed a photo of Rick Mercer in your plane. We're planning at Concordia to send our experiments into this Falcon 20 aircraft. So this is Rick Mercer having fun in weightlessness, not zero G, weightlessness. So the NRC aircraft is already very used to being dirty, so they're fine with us dumping soil into it, right? Now, we're working on a way to keep everything safe and keep our soil contained so that it doesn't escape out into the cabin of the aircraft. But anyway, we're gonna miss Rick Mercer's show once he goes off the air, because he's done some great work showing off what Canada has to offer, including at this episode at the NRC with the collaboration of CSA. So going back to the experiments, that group from Japan, they took this box where they filled it with some soil and they drove a wheel on it. And they did two sets of experiments where in one set of experiments, they applied reductions in weight, pressing down on this wheel, but on the ground, in earth gravity. And then they did the corresponding reductions in weight by going into different types of parabolas with their reduced gravity aircraft. So here we see a graph of the sinkage of the wheel throughout the course of an experiment. So as the experiment goes on, depending on the weight applied, the sinkage sort of settles down into the soil. Now what they found was that if you apply less weight to the wheel, so here for example 3/4 of the weight, so this is a full weight, a regular one weight of the wheel. This is doubling the weight of the wheel. It almost doubles the amount that the wheel sinks down into the soil. If you reduce the weight to 3/4, you get less sinkage into the soil. If you reduce it all the way down to a half or a sixth, you get hardly any sinkage into the soil. And this corresponds with our sort of experience and our intuition on what should happen in these situations, right? You apply less weight to something, it's less likely to sink into the soil. But the key thing from my reading of their work is that when they repeated these exact same experiments in the aircraft, what they found was that the sinkage basically was hardly affected. It's essentially within the experimental noise of one another. It's certainly not changed the way that it does if you change the weight applied here on Earth. So, what does that mean? Going back to this chart that I was showing earlier, so if we're driving on Mars or on the Moon, what happens is that the weight we're applying from the rover goes down, so our frictional traction development goes down, so our ability to perform friction goes down, our ability to produce traction goes down. But our sinkage doesn't go down. So we can't guarantee that the resistance we'll encounter goes down correspondingly to the way it does here on Earth. So this is a driving motivation for why I want to do more experiments like this, where we're going to be putting wheels into an aircraft and doing these tests at these reduced mimicking reduced gravity levels rather than just reduced rover weight. Because unfortunately, this is not the same. Doing a test in the lab with a lower weight rover is not the same as being on Mars. And doing it in an aircraft can get us a lot closer to the representative effects that we're really trying to study here. Now, we don't want to just repeat someone else's research. We also want to learn new things and more things. So in addition to just putting a wheel in a sandbox and putting it in an aircraft, we're going to be outfitting that setup with all sorts of new sensors and data collection equipment. Specifically, I've developed a technique for actually observing what happens to soil as a wheel drives on it. We do this by having a glass wall or a window along one side of our sandbox. We press the wheel up against that interface, and then when we drive the wheel, we can observe what's happening to the soil underneath. Then we apply some computer vision techniques to that, namely optical flow, where we can analyze and visualize how that soil is moving under the influence of the wheel. So here, for example, we have a wheel that's driving in soil, and it has these browsers or cleats, and we can actually observe how when each of those cleats enters the soil, we see a new generation of new soil deformation patterns, and the way that the soil is responding to our wheel is a function of time and is something that we can monitor and study closely. And this is something that I think will enable us to gain much more understanding as to how the soil responds to our rovers. Specifically when we subject that soil, not just the rover, but also the soil, to a reduced gravity environment. So we have upcoming experiments planned. I've been working with Duck, whom I should know very closely, and with Steve. Steve from CSA has been, and his team have been guiding us, and it's an example of one of the ways that the CSA facilitates this type of activity, creating those contacts between academia and NRC in this case, and NRC has also been extremely helpful and very, welcoming and a great partner to work with. And the idea is that we're going to use this technology to help us when we're eventually doing more missions to Mars, maybe even one day working and living on Mars. I'm sure a lot of you have been following closely Elon Musk's talks over the last couple of years. NASA a couple of years ago released their roadmap of getting us to Mars. You've probably all seen The Martian. I don't know if probably all seen the movie. I don't know if anyone has, at least a few of you, I assume, would probably have read the book as well. Yeah, okay, here at least one. Yeah. So one of the things that didn't make it into the movie, that for myself I really nerded out over in the book, was near the end he has this encounter where he's driving a rover down into a crater, and it turns out that the soil underneath the path that he's driving on is not evenly dense, and it ends up flipping his rover. And so that's the sort of problem that I hope to help avoid in the future as we make this journey together. Thanks a lot.